Is it this one? Nope. Is it not that one? Is this desktop 5? What have I done? Why isn't this working? There we go. There we go. Okay, now we're in a business. Okay, folks, how you doing? Good. Until we have to show up to class, right? Feel late? In this room? Show up too late to any meeting. You better have snacks in your hand. You better be out of breath. Okay, so I forgot my clicker. So I guess we're just standing here the whole time. I haven't been able to get to any of your homeworks. I suspect that they're brilliant. I am writing a tenure review packet. And so for the last 4 nights, I've been up past midnight writing. As it's sprung on me very late. But that's okay. We're working on it. So I will grade your work shortly. You should see a new homework. And the new homework is really, really about, determining tidal forces and determining tidal force. So if that section didn't make sense to you or you have questions about it, ask them sooner rather than later. Some of it will be straightforward, just finding out when resonances are in these objects, etc. Today, we'll finish up a little discussion of tidal forces on Mercury, because that's the only planet that has tidal lock with the sun. And then we'll talk in detail about rings. And in particular, we'll talk about how you get structure in rings, because this is going to go back into that idea of resonance. Why does this look like this for us, huh? There we go. Okay, that's better. It'll go into the structure more of why there are rings in the first place, what caused Saturn of rings. We'll get to that towards the end, and what maintains the structure. Is it long-term string? Is this for you? I don't know.
Oh, yeah.
Oh, yeah. I'll get your food too. Yeah, I forgot about that. Okay. So I guess I'll click it and then move. Any questions before? Okay. So let's first zoom in on a little picture here. What is this, by the way? Saturn, right? Anyone understand the lighting conditions here? So this is quite helpful because it helps us see the density essentially. So where places are more dense, like the planet, you can't see through it, right? And you can even see on the backside here, what's that? Why is it reflected? Yeah, what's reflected? Yeah, the rings are reflective and they're lighting up the backside. What are the rings made of? Icy rock. The reason they're reflective is they're icy. Okay, they're not thick. Okay. If you shrink them down to the size of a football field, they're smaller than a paperweight. Okay, they're really, really. Okay. Let's zoom in here. What's that? The moon? Which moon? That's Earth, right? Is it? That's every person you've ever known and has ever existed. Is in what we call the pale blue dot. You ever heard that statement by Carl Sagan? Yeah, that's the image that they're talking about. Okay. All right. So let's really quickly just go back to Mercury. All right, wake up again. Oh, I also need this. What is how many payments and how many sequences? Absurd. Okay. What's tidal locking?
One face is always facing the large object.
Okay. Does it have to be the larger object that's tidal locked?
It could be two bodies can be tidal locked to each other.
Good. All right. So it could be either, but the idea just means that they're showing the same face. So we start with some body, and it's rotating, and another body over here, and it's rotating. Let's say that they're all in the same direction. Okay, so here's the axis of rotation, and they're all going around like this. And let's say this one is going around very fast, shown by the 3 arrows. This one is going very slowly. And the orbit here is fine. Okay. This is much smaller, little m, than this is. Okay? What happens? Okay, so let's draw one more thing here. This will be R. And you're claiming that it moves outwards. So R prime is bigger than R. Is that your claim? How is that possible?
Because the two bodies are rotating.
Okay.
So because they're rotating the same direction, that would increase their orbital radius.
Because they're orbiting the same direction.
They're rotating the same.
They're rotating the same direction. Okay, so they're rotating the same direction like this. Okay. So that means that their angular momentum is up. And the angular momentum in the system is rotating that direction also up. Okay, or out of the board. Okay? Counterclockwise rotation is angular momentum out of it. So, how does the orbit change? What is the mechanism by which the orbit changes?
It's speeding up as big M slows down due to conservation of angular momentum.
What do you mean it's speeding up? What is speeding up about it?
The speed that it orbits is speeding up, and as it speeds up, it moves to a further.
Okay, so we don't exactly know this yet, but because we haven't seen it, but you may remember from 2500. Objects that orbit closer actually move faster. Objects that orbit farther actually move slower. So it's a little tricky there, right? Because even though the R gets bigger, the V gets smaller. But the way that they're related is counterintuitive. Okay, so the angular momentum can still increase by getting farther away, even if the speed goes down. Okay, just good. Okay, so the angular momentum is what's going up here, not just the speed, right? So this thing, the angular momentum we called L. So L prime is larger than L. And that is because the angular momentum of this guy here, little l prime, is less little l. Right? So this thing slows down, stops rotating as much, and it moves forward. Good? Okay. Then what happens?
They will hold each other.
Potentially. But let's say these are just two stars living out in the endless vastness of space, and they have infinite time to be friends.
big alpine, it's orbiting.
Okay, interesting. Any other ideas? If there's no third body, if these two things are not orbiting the sun, what is their total energy state? What are the terms involved in their energy? What? Sure, what would you call that? Right, if we're thinking just 2,500, the simplest way of thinking about energy. Name the energies that you need to consider.
Potential kinetic.
Okay, good. Potential energy of what? What kind of potential? Not quite. Almost there. That would be a kinetic. Because it is moving. Potential is stored. Right, so we have words like chemical potential. Is that what's here? Gravitational potential. Good. So you're gonna have the gravitational potential energy plus what? You said rotational, right? And that's the rotation of each of the bodies. Right? That would be the kinetic energy of the rotation. What else? Very good. The kinetic energy of orbiting each other. Right? Okay. Now this one might be comparable mass to this one, and so they orbit the very center, the common space in between. Okay. Is this thing, you, the total, ever allowed to change? Right? You could have a loss process, right? You could account for maybe the flux of energy of these things cooling off. Maybe there's dissipation due to the fact that you're heating up the body and the body is radiating, but that's going to be such a small amount, right? That we're going to treat that as zero. Okay? That's how a real scientist would think about it, and then they would cross it out right away. Okay. So what this means is that you have to have an interplay between these objects. As the rotational energy here goes down, or the rotational angular momentum here goes down, that has to go somewhere else. Now, thankfully, this kinetic energy is, or sorry, this potential energy is. Yeah, and what is unique about gravitational potential energy as far as the magnitude? Let's write kinetic energy for a second. Yeah.
1/2 mv squared.
Very good. Good. And what's the magnitude? Positive or negative? Good. So this is a positive quantity. All right. What's the potential energy for gravity? No. That's for on Earth, but generally speaking. The mass of the object that you're attracted to, gravity, the big G, not the little g. What else? What? Little m, your mass. Which one? By little r. I'm missing one key element here. Plus. That's not a no. That's a really big important thing. What's the magnitude of this? Negative. Okay. If I trade kinetic energy into gravitational potential energy, is this thing getting more positive or more negative? More negative, right? Okay. So does that make the object more bound or less bound? If I trade the kinetic energy, if I lower the kinetic energy,
What it makes you want. Because it has less energy to like leave.
to leave. Okay, yeah, so let's think about this for a second, right? So this is gonna be a counterintuitive result when we think about dynamics, and we'll have to come back to this in a little while. So maybe I'll leave this and we can think about it. But if I want to go, let's say from here to Mars, okay? And I want to change my velocity. Let's say I'm doing 30 kilometers per second while I'm here at Earth. In order to get out to Mars, where the final velocity is going to be 20 kilometers per second, I need to slow down. I need to change my kinetic energy by decreasing it to move outwards. To go inwards, okay, that would make sense. I have to speed up, right? But this is potentially counterintuitive, right? Okay, we're going to think this a lot more when we get to 2 and 3 body problems. But to take this back to here, and this thing is fully conserved, is there a way to bring this to 0?
Yes.
How?
Kinetic energy has to.
Yeah, these two have to equal. Good. So if they start bound, if this thing starts as one system, can they ever come apart? No. Okay, so when there's just 2 bodies, they're not allowed to come apart. They need a third body to pull them apart. Right? So the reason that we lose the moon is because we have the sun. Okay. What's a system that has 2 bodies and doesn't give a shit about the sun? So the moon and us does care. In a billion or so years, we will leave. Pluto. Pluto has a big body that's orbiting it. Okay, and it's tidally locked with that big body. So just like this one spins down and shows the same face to the bigger body will also get tidal bulges on it, and that will turn it so that they are showing the same face. And at that point, once both of the faces are being shown, right? Remember the torques are done. Now you can no longer convert angular momentum between these 2 types. So the orbit evolution stops. Orbit evolution is only possible when there's a torque. That make sense? Okay. Good. So tidal locking dissipates heat. That's how you get the flexing in the body. And you're looking to minimize those tidal variations. So, when we think about why are there 2 tidal bulges on a planet, the first one, of course, is the obvious one, where it's closer, so it should be pulled more. And the one on the opposite side is the less obvious one. That is because the core of the planet is being pulled more than the far side. So in the perspective of an outside observer, it appears that that bulge is moving away from the body, but the reality is it's being left behind as the core is pulled towards the body, right? Okay. So the results of tidal compression is that you get compression in the perpendicular direction and extension along the axis, right? So you may have heard about spaghettification. Heard about that before? You head towards a black hole. It pulls you at your toes and pulls everything longer. Okay. And then from the perspective of anyone else, it looks like you're being squished and stretched. Okay. You know what it feels like. You're like, ah, fuck. Your toes get ripped off, right? But thankfully at a black hole, you won't feel it. Right? If it's a nice big black hole, tidal forces can be minimum, and then you just get it further. If it's a sharp black hole boundary, and this is the fun part, how quick can your body send a signal that you're in pain? Right? Because it'll be painless as long as the tidal forces are stronger than the ability for information to pass up your body. So it's not the speed of light. I'll tell you that much. It's close, but it's not the speed of light. Right? Okay. Good. So let's look at Mercury. Now, Mercury is the unfortunate son and real close, father's boy, and just sits really close and tries to get all the attention from the dad, and has been trying to do that for its whole life. And so it has been tidally long. So this is the idea that, Venus, Mercury is showing the same face, and so its orbit and its day are the same. At that point, its interior is not deforming. The only reason why Io's is deforming is because it's being pulled on by Europa right behind it. Right? So Mercury is not in resonance. There's no resonance that's forcing Mercury. That's why Mercury is geologically dead. Right? The moon is also fairly small eccentricity. I mean, that is 5% is not nothing, but for the purposes of what we look at. And likewise, the moon's rotation and revolution are also checked. Okay. Here's the stuff that, oh God, that came out really good. Oh, buddy. All right, let's draw this. Let's see if we can draw this better here. So how do you draw an ellipse? Good, but how do you draw an ellipse? That's how I would do it if I had like some magic, box. That doesn't tell me how to draw an ellipse, folks.
Major axis and semi-major axis. Beyond.
Hey, this I'm disappointed in you. You should know this. You draw one X. You draw two X's. You take a string and you put pins in both of the X's. And then you take your pen and you put it between the triangle that makes the string. Okay. As the string is pulled, it will naturally draw out ellipse. Because at every location, this combined distance must be the same. That is the definition of an ellipse. I hate that. What are you talking about? All right, let's simplify it. Let's put both crosses in the middle. Now what do you get?
Circle.
Oh, and it's the same distance everywhere. Right? Okay, this is a fundamental property of the ellipse. And it's shown by this equation. X squared over A plus y squared over b equals 1. What happens if A and B are 1?
Which I think was a circle.
The circle. So x squared plus y squared equals 1 is the equation for a circle. This is the equation for. Okay, so what's A and B? Get rid of this horrifying drawing. Yeah, let's pretend like I mentioned to mess up with this graphic so that I could draw it on my screen. Which axis? Okay, so what's this distance? Focus. So these little X's here have a word, and that's F. This is the focal length. Right? See that there? Here's how you find them. The foci are at plus minus C. Okay. The eccentricity is, let's stretch the circle. So for an ellipse, it is defined as C divided by A. What is it for a circle? What is eccentricity of a circle? 0. Where do I find the focal lengths of a circle? Yeah, right, aren't they the origin? And aren't they 0? So 0 divided by any number is 0. So this still works for a circle. Okay, good. You get it? The aphelion, now this will change depending on whether we're talking about the sun. Helion means sun, and perihelion, right? So aphelion means the farthest point away from the sun. Perihelion means the shortest point to the sun. So if I place the sun one of the foci, where is perihelion? Right. Here. And then this would be. Good. What do we call it when we are not talking about the sun? Anyone know the words? Yeah.
One of the weird one.
You're very close there. Okay, so we have a lot of words. We can use perigee. We can use periaxis. Those are fine. We'll see it. But this is what you're looking for. Peri and aph. 2 and 1. That's what it looked like. And then you can't see the picture. All right, here's the orbit comparisons. Circle in the top left. Mercury, pretty significantly elliptical. Right? It's 20% ellipticity, much more than the moon. That's essentially what it looks like for the sun. There is certainly some variation in the interior of Mercury, but Mercury is mostly core, right? So the ability for it to flex and change, I think, is quite different than if it was say made of ice. Ice is much easier to deform, and so you can get something like Europa having a surface that is constantly warmed by tidal heating, where you don't get that from Mercury. So people used to think that Mercury's rotation and revolution periods were equal. And I just said that to you, and no one said, wait, what? Because if you recall, when we looked at the Mercury fact sheet, the day and the year weren't different. And yet I claim they were tidal wrong. Right? What's going on here? Hope I have it here. In the 1960s, we showed that the rotation period of Mercury is actually close to 59 days. Okay? So if you look here, the revolution, the year, is 88 days. And they were using radar, bouncing it off the surface and looking at the signal that comes from the rotation of Mercury. And they said, actually, the periodicity of that signal of watching this thing rotate, and there are going to be dark spots and light spots. Watching those light spots go up and down and up and down and up and down, they said it's not an 88-beat period. 90. How could that possibly be? And it turns out that if you account for the fact that it's flexing, and you account for the deformation that, we talked about. Oh, I deleted that. We talked about the tidal deformation here. There is a state where instead of pointing your face directly at the object, in an eccentric orbit, you can show a ratio of those faces. So what do I mean by that? The orbital period is 3 halves the rotation period. So what does that mean? The orbital period is longer, right? Okay, so let's watch it. Okay, so let's do I'm gonna draw that. Here's Mercury, and let's put a little dude on it. Okay. And let's watch it throughout the course of an orbit. How many orbits do I need to go around for it to show the same thing? The orbital period is 3 halves times the rotation period. So if that is the case, the orbital period is 1.5 times. Where is Mercury when it shows the same face to the sun again?
Have to be in orbits 2 times.
The other side, the other side. It'd be on the other side of the second, or the opposite side of the second.
On the opposite side of the second orbit. Let's reread that. The orbital period is 3 halves the rotation period. So the thing rotates 1.5 times every time it goes around. Right? Think about that again. So where is it? Right, the period is longer than the rotation. It rotates 59 days. Going around.
They still have to go around twice.
No, I'm asking for the very first time it shows the same face.
Oh.
I mean, obviously, yes, it will show up here again 3 times later, but that's not what I'm asking.
Yeah.
I think you're thinking about these backwards. Think about the numbers again. Okay? Year, 88 days. Rotation per day. It's gonna be stupid, but just bear with me. 59 days.
Oh, did you want 2/3?
Ah, 2/3 of the way through. So that's like here, right? Oops. Right? Okay, and then 2/3 after that. You sure? Okay, so if this is 2/3, and then I do 2/3 again. This 1/3 gets me to here. 2/3 gets me over here, doesn't it? And then on the third go around, I get back to ourselves. So there's 3 points in the orbit where it points to face the sun. 3 points in 2 orbits. Okay, so it starts here. start. T equals 0. Then it goes over here at T equals 59 on the first orbit. It skips by this, comes to T equals 59 times 2, which I'm just for the purposes of this, I'm going to say 118. Okay. And then 118 plus 15. 176 of them. See? That's helpful there. Let's put yes and can you see? Yes and Spanish. Can you see English? Right? Okay. This is the configuration I rendered. It's a weird one. It's a weird one because it is very eccentric orbit. Okay. All right. Mercury's slightly oblong. It's not a perfect circle. So it looks like that. That's obviously exaggerated. And there's a part that's being pulled towards the sun. Sorry. So the fun thing about Mercury is that not only is it elliptical, the axis of ellipticity, what I mean by that is, let's say that this is the, this is, call it A minus C on this side, and A plus C on that side. In the ellipse. And we have, let's say the Earth is going around way up here. That's us. Okay. So as we look at that, we say, oh, Mercury's going around, it's going around, it's going around. But in fact, this whole thing is rotating. And we can watch as A minus C rotates. Okay. The weird thing about that, that is called the precession of an orbit. Okay. And that happens, kind of frequently. So for example, if your spacecraft goes into the atmosphere, it's going to dissipate energy and the orbit's going to change, right? And so people were wondering, why is this thing rotating by how much that it is? They could explain some of the precession due to the fact that Jupiter is kind of tugging on it and slowing it down at times and making it rotate in weird ways. But they were like, something really strange has happened. And this fellow from Germany came along, and he was riding a bunch of trains and looking at clocks. And he was like, hey, I think that gravity is curved. And everyone was like, what the fuck are you talking about? And he's like, mass, like I think that that is just the curvature of space-time. They were like, what the fuck are you talking about? And he was like, I bet that if I looked at the sun, I could prove why Mercury rotates as much as it does. And he did. General relativity is necessary in order to understand why the precession of Mercury exists at all. There is a huge component that comes into the fact that that the space itself is curved toward the sun. So as it orbits in a curved space, it is going to rotate because of the curvature of the space is so large. Now, other planets, of course, have this as well, but because the farther you move away from the sun, the curvature goes down dramatically, it's less noticed. So the two things that led to the precession of Mercury being identified, one was the fact that it's much closer, and two, it has a large eccentricity. Two other things that prove general relativity. One, the timing of stars eclipsed by the sun. It's a very hard measurement to make. Okay, so what do I mean by that? All right, I'm just going to go on a tirade really quick. Here's the sun. Here's the background star. Okay, we are moving. So as I move left to right, it'll look like the sun is. Okay? And so the sun will block out that star. Okay? And what I'll get is I'll get the combined light from the stars, and then one goes in front of the other, and then it comes back. Okay? And that's called an occultation. Okay. So Mr. Einstein claims that he can bend light with space. So it shouldn't look like that. It should look like a curve. Okay. Made some think about it. Okay? Some people are like, "Wow, sounds great, Albert, but like, what the fuck are you talking about? We can't look at the sun. We can't look at stars. Right? You're gonna blow out our telescopes." So what do you do? How do you figure out?
They like take a picture and with the stars in the background, they would work because of the fact. Because of the sun.
Yeah, how do you take that picture? The sun's in the light. In front of the sun?
In front of the telescope.
What was that? You got a natural screen. Screen the whole planet. Right? With the screen that's close, one of the biggest issues you're gonna have is it's gonna bend around the screen. If you put it far away, then it won't bend as much. So they looked during an eclipse, and they can see the light from stars bend around the sun. So then they're like, man, this guy knows something. You really got to figure it out. Okay. So this is one of the first triumphs of general relativity, but that was the second. Okay. Okay. That's it. That's all I have for Mercury. Mercury's fucking fascinating from the perspective of orbital dynamics, from general relativity. We can understand that if anyone wants to take general relativity next semester, but I don't know if, did you guys take EM 2 already?
Yeah.
Okay. Cool. Okay, so let's talk about rings. Yay, rings. If you like it, then you should. Okay. Which planetary systems of the gas giants don't have rings?
Yes. They all have rings.
They all have rings. Got him. Got him. All right. So let's understand what the fuck these are, why they're so ubiquitous, right? The first rings were seen by Galileo in 1610. Why did it take so long? Because far, that's exactly correct. So why did Galileo do it? Telescope, big old telescope, right? It's actually small. You can see it with a very minor telescope, right? And you can see that there's rings. So the small one, this is for a man. What do rings look like to Galileo? Anyone know? So here's what a star looks like in a telescope. Okay. Here's what Mars looks like in a telescope. Okay. Here's what Jupiter looks like in a telescope. Okay. And here's what Jupiter's moons look like in a telescope. Okay. You see where I'm going yet? Here's what Jupiter's rings look like to Galileo. He had a small telescope. And it wasn't until Huygens came along, much later, almost 40 years later, 45 years later, that they made the telescopes larger. The reason why this is important is hard. You have to grind glass. In the old days, my grandfather used to tell me about this. When he was in grad school, they would grind the glass themselves for their telescopes. Fun. They didn't have TikTok. Fucking morons. Okay? And so finally, you could see that it was like this. Something was going on. Right? So by the time that your telescope aperture gets large enough, right, you get a really big telescope as opposed to a small one, you can see that there are. Okay. There are many flat rings. Okay. They all go in the same direction. Oh, there you go. Remember I said earlier it was wrong, not football field, what is this, what is a freedom? What's the sign of freedom? Yeah, about 70%. So next time you're driving a mile, start your odometer, wait for it to get to 0.7, and then look back and imagine one paper the whole way. Okay, so that one piece of printer paper is the width of the rings. Okay. If we look carefully in those gaps, and we're going to see some pictures of it, turn the lights off and everyone will fall asleep. But the rings themselves have gaps. So we need to understand what the fuck those are. Why are there gaps? Why are they not continuous? And then sometimes we have small satellites, sometimes called moonlets or shepherding moons. Okay. They match mean motion resonances. We'll talk about what those are in a few seconds. And they're almost all waterless. So some of it is rocky, but a majority of the material is waterless. That's what makes it fun. Okay. Saturn. Beautiful, right? This is not even very good. I guess it looks fine. We can find higher res photos and we'll look at higher res photos later. What are the main features you see? Yeah. Where do you see gaps? Right.
There's like the black band.
Here.
Yeah.
Yeah, you think that's a gap. Okay, good. Is that it?
There's a lot of.
Where?
There's a lot of more visible. Like
Here? Left or right?
right. Very.
There?
Yeah.
Yeah, there's also a gap there. Right, what else? Ah, there's an empty spot. That's a big old gap. What else? No, we don't care. The Saturn doesn't exist yet. Just looking at
I'm
rocks.
just saying that they are all on the same joint.
What do you mean by that? Oh, these ones here?
Yeah.
Yeah, they're rotating the same direction. That's a very astute observation. Okay, that's not what I want though. You don't know that atmospheres exist yet. Their color difference. Why the fuck are they colored like that? Well, we can assume that, right? But do we have any reason to believe? Or just think about this ahead of time. Let's say you don't know how they're made. Okay, and you take some rocks, you go home tonight, smash them up. Okay, you get all the same color. Okay, weird. Let's say you take a bunch of rocks from different places, you smash them up. Now you got a whole bunch of mixed up rocks of different colors. But this looks like the interior here is dark and then light and then dark again. And if I go up here, it looks dark and then light and then dark again. So why isn't it the case, as I go around in the rings, why aren't the colors mixed? Like, why isn't there like a little spot here of light and then dark and then light and then dark? Isn't that weird? Okay. So let's zoom in here. We're going to zoom in on the right-hand side. Shit, now those gaps gapping. Look at that. Anything else? The what? Where? So, yeah, that's a dot. Good. What else? Here.
All that too. Right there.
Yeah, that's something, right? That's probably. Here, yeah, get these ones, yeah. That one.
What is the brighter? Go down.
You going?
Yeah.
This? Anything else? What's up, docs? Cool. This stuff, right? Look at all those fuckers. We called that a gap. That's not a gap. There's rings. Look, I can see 1, 2, 3, 4, 5. See 1, 2, 3, 4, 5, 6. Okay, okay. This is like when you get outshined by your more beautiful sibling. Like, oh, so pretty. Maybe forget about you. Okay. Let's zoom in some more. We're going to zoom into this region. And finally, we're going to begin to talk about the names. They are stupid. Okay, so the outer ring is called the A ring. The inner ring is called the B ring. Then we found the C ring. That was the interior. But we fucked up because there's rings outside. So there are the F rings and the D rings. Okay, so we'll talk about all of them. In the middle, okay, that gap that you pointed out is called the Cassini division. That separates ring A from ring B. And of course, that's kind of a shitty approximation. Because if you look inside, there's no fucking ring. Right? It's running all the way down. What?
We need a ring G.
We'll see. There might be. Let's relax. I mean, this is a big ring system. We got plenty of letters, okay? We also have some words here. This is the empty gap and the cubic gap. And this really looks like a gap, right? That looks like a real hole. We want to find out why. Okay. The Cassini division, this here, this is an orbital location. So us to destroy here. All right. One thing I want us to remember is there is a relationship. Okay, as I go out in distance. Okay. Let's call this the period P. How is the period P related to the semi-major axis A? When the period gets bigger, the semi-major axis gets smaller. Is that true?
Makes longer to get around. Yes.
Right. But as I move away from the body, my period of rotation goes down. Are they 1 to 1? No, whatever. And whose law is it?
Isn't it Kepler's?
It is Kepler's law. And what is Kepler's law? Astrologers or astronomers? Come on, folks. What's Kepler's law? You'll be able to guess it. N here, and I'm gonna put N here. want to know by the end of class. Okay, so the idea is that I move away. It takes longer to go around. That's not that strange. But if I'm closer in, then I'm going to be creating mean motion resonances with other objects. So if I am, say, at this location, where it takes 4 hours to go around, and this location where it takes 2 hours to go around, I am in what kind of resonance? 2 to 1. This body goes around 2 times for every time this body goes around. This is a 2 to 1 mean motion. Oh, fuck, that's one.
It would be the other way around, too, because it takes 2 hours for one body to move around, but that go on 12 for 4 hours.
Right.
So,
Yeah. Good. So this gap exists. This Cassini division exists. And it just so happens when we look at, let's say there's a particle in here, we can figure out how fast it's moving around Saturn. We measure that, and we compare it to the speed of a moon called minus. We'll see minus a little later in the semester. And we compare the two, and we see that this gap, if there were a particle there, is going at a 2 to 1 mean motion resonance with minus. So it goes around twice for every time minus goes around. Okay. Let's zoom in a little bit more. I want to look at the Keeler gap. Whoa, what is that? Little shepherd moon. And what's it doing? Shepherding. It's a fucking moon. So as it goes through, as it moves through the rings, let's remember how this is oriented for a moment. Which direction is towards Saturn? Up, right? So this is the interior of the rings, and this is the exterior of the rings. So let's imagine, let's go into the reference frame here of this moon. You're standing on the moon. Which way do you see the rings go? You're looking at Saturn. And at Saturn, this material is moving faster, so it's faster. So it's going to be going this direction. Let's say you're sitting, moving faster than you. It'll appear to go. What? So let's imagine, all right, this is all the rotation from above. Okay, here's Saturn, here's the ring, okay, and then here's you.
What it look like the front of you is like getting away from you, the behind you it's like.
Don't look at behind you, just only look forward. Looking at Saturn.
left.
Left or okay. Now look. Which direction is that going? Now look, you're looking behind you, you're looking down. Is that what you meant by right to left? Okay, all right. Okay, that's fine. This is a confusing thing because if you're in the ring, you have 2 different groups of material going in 2 different directions. If you're in contact, that's called shear. Right? Shear is when things pass by one another. So tectonic plates that move by each other are shearing each other. Okay? In this context, we are the moon. We're in the reference frame of the moon. So we only see the moon and stuff moving by it. And so we see an unperturbed ring. And then it encounters the gravity of the moon and it gets pulled. And it creates a wave. And that wave wiggles for a little while. And then eventually it settles out because things bump around and they touch each other and you get rid of that energy. And then it moves straight again by the next time you sit. But in this direction, the disturbance looks like it's going the other direction. Because from this perspective, these rings are moving that way in this direction. Okie dokie. So that's the Keeler moon gap ring thing. Here's some more. So that's Pan. Pan is cleaning up in there. So creates this gap. What happens if you're a little dust particle and you want to go there? Yeah, probably get smacked in the pan. Or you get too close to Pan, you get thrown back into the rings. Right? Pan is cleaning. We'll talk about hill spheres a little bit later. But Pan cleans. The Keeler gap, I think it's called Keeler. Cleans. Okay. On the right hand side, these are. Is this my actual house? Hopefully it's not in the image. Yeah. Okay. Good. It looks a lot like they're just reflected material here. So it's really hard to tell the density here. But even in these regions, you have density waves. And these waves are going to be reflective of the fact that this material it's obviously interacting gravitationally with the body, but it's also responding to everything else around it. Okay, so when it bunches up and creates an overdensity, then it pulls on stuff nearby, right? And grabs it into basically spiral density waves. And so the more dense that you are, the more that you can clean up your nearbys. Okay? There's two ways of cleaning the rings. You have an object that's flying through there. And remember, all of these are moving at different speeds. So just like if you were walking around on campus, if the flow of traffic is all going in one direction and you start going in a different direction, let's say you're a little piece of rock and you fly by Pan and Pan kicks you into the inner gap system. Well, what's going to happen almost right away as you go through the gap, you clear the gap, you make it to this part of the disk, and now you're hit with an onslaught of people going in one direction. Now you start going in that direction. So these are corrective behaviors we see in the gap. Oh fuck, we didn't make any progress today. Okay, there's Saturn's rings. There's this really cool radial spoking. Yeah, you can see it here, right? I mean, even though that's cheap, it's better on the computer. So these are, when we talked a little bit about, do we expect the rings to be uniformly dense? No, we don't. And there can be entire regions throughout the rings where the density varies as you go through. Excuse me. Okay. And you can even see them here. Right, you can see them as they move around here to here. Yeah, here. Here. So you can see these overdensities in the rings themselves. Okay. Here's the names. Remember you wanted a G ring? You get a G ring, and you get a G ring. All right, it's out here. And this is the radius. So one of my favorite jokes is like, fuck they named this, right? So you get the Saturn equator at 60,000 kilometers. And then the D ring's inner ring is right there. Right? It's at 66. So that's the Cassini division between A and B. There's a Titan ringlet at 77. Okay. The C inner edge, the D inner edge, all the way out to E. Okay. The thickest part of the disk is here. Right? At the A inner edge. It's really bright one. That's 30 meters. Cool. Questions, comments, concerns? Okay. I'm gonna show you a little bit outside. Yeah, wait, let me. So I guess we're not gonna really talk about it here. Maybe we'll talk about it when we talk about the moons. What causes the E ring? What causes the rings? What? I heard two things: outgassing moons and satellites. What do you mean satellites? Yeah, so one of the biggest questions that scientists have been asking is, do the rings, are they increasing in size? Are they decreasing in size? Are they new? Are they old? I've only told you the structure of the rings. I haven't told you anything about their age. Okay. What if I told you that the rings of Saturn are younger than sharks? So is that weird? Why?
So. I mean, sharks have been around for a time, but Saturn, well, like, you would expect the rings to collapse very quickly.
Okay.
Um,
Do you expect the rings to collapse quickly, and why?
Yes, because,
No, no, why?
Why?
That's okay. That's okay. We're gonna get to those intuitive feelings, right? So you have this feeling that the rings are ethereal. Why is that?
I'd say that they get sucked up on the moons or form different.
Okay, right. So let's say there are moons, right? And those little moonlets, they've done, right? So like we saw Keeler. Keeler did what Keeler can do. Keeler's not grown. Dan's not grown. Okay. We're gonna think a little bit more about that. I'm gonna leave that as a nugget for you to really reflect on why do we expect rings to disintegrate. And interestingly enough, E is the only ring that's being replenished. And that's by Enceladus. Coincidentally named. Okay? Enceladus contributes to the E ring. Let me show you more, because the ring system is fucking massive, and you didn't even know that. You just see this with your little eyeballs, but here's the E ring. What's that? That's Enceladus. Doing its little thing. Spurting off into space, all this fucking stuff. Okay? And it's not even the end of it. Here's Titan. Titan's outside of Enceladus. Here's Iapetus. And here's Phoebe. Phoebe's fucking far, bro. And there's a giant ass ring. Okay. So Phoebe's a weirdo, and it goes the wrong direction. It's not the wrong direction. Phoebe thinks that's the right direction. You know, we don't judge it. But the rest of them are, you know, mostly regular satellites and mostly going in the prograde direction. This is going in the retrograde direction. And, you know, Phoebe's kind of like a strange one because it's not even fully circular. And yet it's probably an icy body that is liberating stuff off of its surface. So as the ice is exposed as it's tumbling, it's sublimating. Now it's not sublimating so rapidly that it's like a comet where it loses significant mass of its fraction of its mass with time. When we see comets, we'll see that they only have a limited number of times coming close to the sun before they run out of its orbit. So you will see that this one here just slowly losing material, and then it kind of, you know, it's not being directly pulled into Saturn, it's not being pulled to someone else, so it kind of just like hangs. And it forms this like ring, this torus of like fuzzy material. Not fuzzy, hazy. Okay. Iapetus is cool. Hopefully we'll get back to Iapetus and do moves. Questions, comments, concerns? Okay. Yeah, we can do this. Maybe not. Uranus has rings. The second ring system was discovered in 1977. They used the Kuiper Airborne Observatory. It's just a really sick way of like saying that you want NASA to build you a cool plane. Then you put a telescope in the plane, you fly up really high, so you can get above Earth's water. And you take really cool observations. They found it because of that occultation that I told you about before. And so they can use the same phenomena, stellar occultation, and just watch a star go behind Uranus. And when they do that, instead of seeing this, you see this. Right? It passes behind the ring occults the star, the light goes down. And then you see the star again, like, what the fuck, why did this star just become dark for a second? And then it passes behind Uranus, and it's really dark, you don't see the star at all. And then you see it again, and you see it twice. And because they can look at these distances, and they can say, well, was there a moon there? Did we happen to see a moon? Oh, no, they tried again, they tried again, they tried again. They always get them at the same locations. Ah, it must be a ring structure as opposed to right? There are 10 rings discovered from here, but they don't have, they don't have the same like. Okay, they have really cool structure. I want to show you them before we run out of time today. Here's Saturn's rings. And again, I told you that was second naming things. They are epsilon, delta, gamma, nu, beta, alpha, 4, 5, 6. And you can see some of them here, right? So from the outside, they go in. So the bright ones are out here. They go in. So you get epsilon, delta, gamma, nu, beta, alpha. And then you got closer and you realize, oh, what about 4, 5, 6? Okay. We can zoom in here. Let me just show you the structure. Okay. They're real thin. Real thin boys. And if you take a long exposure, you can see that there's material there, right? But it's really not thick. So these are the background stars. You take a long exposure, spacecraft's moving, stars move. Okay. We can ignore anything like that. But you're moving with this system. So you're staring right at it. So it's not supposed to move. And yet it's so thin that you can see even the thinnest background stars there right through it. Where what's really cool about Saturn's rings, of course, is that they're so thick. They're not that thick. But they're thick enough that you occult stars. Okay. What else? Here's the ring structure. Let's talk about Jupiter's rings. Neptune has rings, but I don't think we'll talk about them here. No, we'll do it next time. It's got rings. Jupiter has 6 rings too. David Steve has great pictures. I'll show you those. Questions about rings before we go on? What's Kepler's law? You let the geologists tell you about astronomy and be right? Come on, books. Step it up. Tell me what Kepler's law is.